There are many great things that we learn at school and things that we learn at the university. How to design electrical systems. We learn the tips and the tricks, and we know exactly how to design a circuit. And one of the good things that we learn is impedance matching. You should match impedance, is what I learned. But on the other hand, it's quite often also important to learn when we should do that and when we should not. So today I invited the biggest matchmaker in town, Professor Peter Baltus. You worked on microelectronics, and that's exactly the field where impedance matching plays a quite important role.
It's one of the fields indeed. So thanks for the invitation. I really appreciate it. And indeed in microelectronics it plays an important role. Actually, often it plays a bigger role in discrete electronics. Because one of the areas where impedance matching is really important is if you have long connections, longer than the wavelength. In microelectronics, the connections are very short. So in fact, one of the things that we have to teach our students when they just start is that they should forget about this thou-shalt matching theorem if it's on chip and nobody can see it, right? If it's not going outside. Very often it's more optimized to go for a different impedance, for a mismatch, than for a matched impedance.
So let's see what we can learn from this. I still hoped that asking for an analog person who has experience in analog design with Philips Semiconductors, with NXP, and now with Eindhoven University of Technology, that you're the right person to talk about it.
Oh yeah, I love talking about matching. I mean, I'm not saying you should never do it, but it's maybe, yeah, it has its place, right? Some places it's more important than others.
Now you already made a big step. You're not saying you should never do it. Well, let's see when you have to do it and when you do not have to do it.
Okay.
Because there are instances where you should not match impedance. Well, I've bought a couple of things that you may recognize.
Yeah, looks like an antenna.
That's an antenna. Would you match the impedance?
Yeah.
And
for receive, right? It's a receive antenna.
Well, it has one connector, but it is transmitting and receiver. Why does that make a difference?
It does make a difference. For receive, you want to extract as much power out of the antenna as possible. Right? So the reason that the thing that you optimize for is to get as much signal from the antenna as you possibly can, and that means matching. That's the best way to get all the energy out. For transmitting, you're not necessarily trying to get all the energy that's available from the transmitter into the antenna. Many transmitters for wireless systems, they prefer not to have a connection to the mains outlet, because then you have, again, a wire. So often they run on batteries. And then the optimization is not to get as much as possible energy in the antenna, but to get that energy there at the best possible efficiency. And that efficiency is often achieved not with matching.
That brings us to an interesting debate, because I grew up in the time that I listened to medium wave radio, Radio Luxembourg, blasting a megawatt and more into the air. Yeah. And then power efficiency is the key thing. And now you're saying it's not about the efficiency. And that's
for the transmitter it is about efficiency, right?
Yeah.
But especially the efficiency means that you're not necessarily matching. Because if you match, then you dissipate as much in the source as in the load. So you dissipate as much in the transmitter as in the antenna. So if you have 1 megawatt coming out of the antenna and you have matched transmitter, then the transmitter will dissipate at least 1 megawatt in heat. That's not
Which is a
what
lot.
you want.
Exactly, it's not. Before we dive into the details, Peter, what does the impedance matching theorem says? You have been teaching this, so yes. I give you the honor of explaining what impedance matching means.
Yeah, so you get the largest amount of power out of a source if the load impedance that you connect is the complex conjugate of the impedance, the source impedance of that source.
The biggest amount of power, you're not saying highest efficiency.
No, it's not the highest. It's arguable that it's by definition not the highest efficiency.
By definition not. And there's also another point that is intriguing. You're talking about what to do with the load to get the most power out of the source. Yeah. You're not saying how to make the source to get most into the load.
Both is true. This is how it's traditionally taught to our students. But of course it's true. If the load is a given, then you optimize the source and vice versa.
Okay, and then you also said complex conjugate.
Yes.
Which is basically saying if you just talk about ohms and resistances, they should be the same.
Yes.
If we talk about impedances, inductances, or capacitances, then it should make sure that there is not too much blind current wasted.
And there's no blind current wasted if it's matched, right?
Not too much. Okay, let's go through the list then of to match or not to match. Connected to this antenna, there is a piece of wire.
Yes.
Does that matter? Well, maybe here I have another piece of wire. Coaxial cable.
Yes. Yeah.
People call that this is 50 ohms.
Yeah, well, that probably is 75, in fact.
Indeed. Yeah. Can you measure the 75 ohms for me? No.
Not
But you have a meter here.
this one.
So it is
different equipment. Yeah.
the tricky thing about these long cables is that if we make it very long, there are inductances in here, there are capacitance in here, and then it looks like the cable sucks like a 75 ohm power into that very long transmission line.
Yes.
Should I match it to 75 ohms then?
Yeah.
At the end or at the beginning?
Okay, so it depends what you want. Right? It depends what the criterion is. So if the criterion is that you don't want reflections, then you have to match at the end. Right? Because if the signal comes at the end and it's not terminated with 75 ohms in this case, then part of that energy will be reflected and travel back. Then if the requirement is that you not only don't want reflections, but you don't want an infinite number of reflections, then you should at least match at the source. But if you don't care about that either, then you don't need to match on both sides. If you do care about both, then you have to match on both sides. But again, it depends on what you're trying to achieve. There are places where you, like with the transmitter, where you intentionally do want mismatch in many cases.
Now, when we match, I sometimes have difficulty in understanding what an output impedance means. Yeah? Because in the models we see that it's more like a resistance in series with the power source. But most of these power amplifiers have a push-pull transistor with feedback, and the output impedance virtually is zero. If I pull a load there,
not
then
quite zero, right?
Not quite, but not 50 ohms.
No, not 50 ohm at all. No, indeed, and that's again because you want mismatch in this case. Right? If the output impedance would be like 1 ohm, and you're driving a 50 ohm resistance, then you're dissipating in this 1 ohm 1/50th of the voltage of the load, and therefore 1/2500th part of the power. And so that's what you want. You want all of the power that you generate in this transmitter to end up in the load and not inside the transmitter itself. At least in most cases, unless it's really, really cold, right? Then, okay.
Okay, I've got an amplifier here, and it says 50 ohms.
Yeah.
So the output impedance of this, is that really 50 ohms?
Not necessarily. It means that people expect you to connect 50 ohms to it, which is something different than that it is 50 ohms. So that means that it achieves its specifications when you connect a 50 ohm load to it.
So in fact, to be efficient, most likely it's much less. It's this kind of push-pull transistor. The output impedance is much less.
Yes.
We are not supposed to load it with something else than 50 ohms. Now we see a lot of radio amateurs and people being proud of having a standing wave ratio of 1.00. So it's exactly 50 ohms.
Yeah. And that's not necessarily...
Should I be proud of that? Or
for receive, you should be very proud.
Yeah.
Because you still get as much signal from the antenna as possible. For transmits, depends. If you have a transmitter that's optimized for 50 ohms, it might still be a good idea to optimize for 50 ohms. So for a very low VSWR, because then you'll get the thing according to spec, right? And the transmitter does what it's supposed to do. You might be able to get a little bit more power out, or a lot more power out, if you change the impedance, but you might destroy the transmitter, which is often not a good thing. You might generate distortion and spurs at other frequencies, which might earn you a visit of the Rijksdienst voor Digitale Infrastructuur, right?
Used to be the radiocontroledienst when I was young.
Indeed, and these people are very friendly, but they have a limited sense of humor for that kind of thing. So it's still a good idea to try to match with what's specified.
And what have I always understood is usually there is also a filter, in particular, to satisfy all these regulations. Filters with capacitances, with inductances, and if you're not careful with loading the antenna after the filter, you get a lot of reactive behavior where currents get out of phase with the voltages that come out of it.
And then you get distortion and or you destroy the transistor.
We'll get back to this one when we talk about communications via LEDs.
Good.
Because then it becomes interesting to see how to connect that. Shall we continue our story? I have a loudspeaker.
Yes.
Do you like HiFi?
Yeah, sure.
Do you match the output impedance of
No.
your amplifier? You don't do that?
No. Again, it's efficiency, right? And its specifications as well. You want to load the amplifier with the impedance for which it's meant, but that's usually not a matched impedance.
I like HiFi. I like Phil Collins, and when he's kicking the drums, I really like to have that pure sound.
Yeah.
Not some. And there, what I learned is that there is a magnet in here. There's a coil in there, and if Phil Collins hits the drums, then the whole thing starts to resonate.
It does.
And in order to stop that resonances, you just make sure that the output impedance of the amplifier is low, such that you really control what the speaker is doing.
But again, it depends on how the amplifier is designed, how the loudspeaker is designed, and it depends also on the acoustics of the room in which it's put, of the enclosure in which the loudspeaker is put. So it is a lot more complex, but essentially, yes. You need to use, if you want things to behave the way they're designed, you need to use them in the way they're designed.
Okay, let's continue our story.
Yes.
You have this in your house as well. Do you match impedance on a wall socket?
I had a discussion with a good friend of mine, Lucas Leijten, about that. He is an electromagnetic background, and when he was young, he was a true believer in matching. So I challenged him. And,
when he was young, yeah. But he grew up wise?
Yeah.
Okay.
Yes. There's... So you definitely do not want to match that. The goal is not to get all the energy out of the mains that you possibly can, because it will upset a few things. To start out with your fuses, maybe the wiring, and maybe even the electricity provider.
You don't want to spend 50% of the power in the grid, in the net itself.
I mean, it's designed not to.
Because if you would match, then the output voltage would drop to half. Is that why the Americans use 110? No, apparently not.
No. But it's an interesting concept. Yes, I haven't thought about that. But no, you should definitely not match.
Okay,
this is very low.
So maybe we wrap up and see that basically there are moments when matching the impedance is a good thing, and where it's really an advantage to train these things, to know how to do it in the design of microelectronics. And there are also places where we would not like to match.
Yeah.
Having said all this, I would like to move on to seeing what would be a good thing to do if we work on optical wireless communication, where we feed a signal into an LED.
Mm-hmm.
And for that, I would like to go into a second episode. Okay, so we continue our talk with Professor Peter Baltus on impedance matching. Mm-hmm. How should we load a device when we attach it to an amplifier, or how should we design the load if we have an amplifier? But we are talking about optical wireless communication, where we want to modulate an LED. Now, I have an amplifier, and we have some LEDs. Mm-hmm. And what I see happening is that many people in scientific papers just connect these.
Yes. Yeah.
And I see you smiling, because I see that in many scientific papers. Oh, by the way, they do impedance matching because there's a nice 50 ohm cable, there's a nice bias T, mm-hmm. and then there is this LED.
Yeah. Yeah, I mean, something will happen for sure, right? But the question is that you don't know for sure what is going to happen. So as long as the amplifier is not destroying itself, and many of those more expensive amplifiers, like the one that you're holding, they're fairly robust, so they might not immediately destroy themselves. And if there's not too much power coming out, then if the power that it generates is limited, then it will also not destroy the LED. But that's about the extent of it. I mean, it's in no way optimum. You don't even know exactly what is happening, because you're using the amplifier in a situation for which it's not specified. And equally, you're driving the LEDs with a signal that you don't know.
But what I see in many papers is that the most expensive lab amplifiers being used, and I see specifications of all kinds of things like the distortion, blah, blah, blah. And then they drive an LED, and you say it's very ill-conditioned.
Yeah, it's worse than ill-conditioned. You really don't know. Unless you measure what's happening, you really cannot predict what will happen, because you don't know what's inside this silver box that you're holding.
And that has a lot to do with exactly what we mean by output impedance.
Yeah.
So it could be that it breaks if you load it with something less than 50 ohms.
Yeah.
But it may also be that actually the output impedance is relatively low, and then you feed a huge current into the LED.
Might very well be. In fact, you could also destroy some amplifiers by loading it with more than 50 ohms, right? Because voltage might get too high. So there's many ways for things to go wrong, and the chances of things going right, exactly like the amplifier was designed to, is fairly close to zero.
Now, what I find interesting there as well is that when we have an LED, I see a lot of LEDs for illumination being driven by a current source. So the idea is that a certain current is dictated that goes into the LED. That's also for good reasons.
For really good reasons, yeah.
Because all the world thinks of voltages. What the grid gives is 230 volts, and then suddenly with LEDs we have to think in currents.
Yeah. I mean, the LED is a nonlinear device, and in theory there's an exponential relationship between voltage and current. So if you get the voltage a little bit wrong, you get and your voltage using the voltage as a drive, then you get the current a whole lot wrong. Right? So because it's exponential. So and the LED output is more proportional to the current than to the voltage. So if you have some need to get a fairly predictable result, driving it with a current makes a lot more sense.
That's what we see in most of the implementations of LED LEDs. But when we see scientific papers about LiFi, we see these amplifiers feeding apparently a voltage, a relatively low impedance on the LED.
Very likely. But of course, it's through a coaxial cable. So it depends on the frequency and the length of the cable. You even don't know whether it's a voltage, right? It could be anything. Because if you're a voltage, if you're low impedance, and you're making a long cable, then it's going to travel along the Smith chart, and you're going to see all kinds of wonderful impedances. You really don't know what you're doing. I think that's.
And I must admit that I didn't believe that story until I started to do the calculations. The dynamic resistance, that is the resistance that a modulated signal actually sees when it feeds a current into the LED, is quite low. It's 0.1 ohm. It's 1 ohm or so, because of the steep curve that we see as voltage versus current versus voltage. So we see these very low impedances there.
They're low impedances. You can only talk about it if you have small signals, because it's a nonlinear device. Right? So if you drive it with a sufficiently large signal, then you cannot even talk about an impedance anymore as a constant number.
Yeah. And then we have this very low impedance in the LED. We have a low output impedance from the amplifier. Assume that the amplifier survives this. Then we have maybe a piece of wire of this length.
Yes.
And that really makes a difference if we talk about impedances of half an ohm.
Yeah, it depends on the frequencies. Right? So if it's short enough like this, and you have wavelengths of hundreds of meters, then it doesn't matter. Yeah. But in practice, and
we modulate the LEDs up to 100 megahertz, a gigahertz or so, and then these pieces of wire
they start to act like a transmission line. Yeah. That's what they're designed for. And at 1 gigahertz in vacuum, the wavelength is 30 centimeters. In a cable, it's a lot less, right? Because it's the dielectric constant of the cable. And then you start getting, I would say, pretty close to a quarter wavelength or so.
So then the question is, we want to drive the LEDs, we want to modulate them. Then basically what the academic world is doing is have a very expensive lab amplifier. Just having something with a couple of transistors soldering it yourself gives a better conditioned experiment, better repeatable by others. So we need to come to your office and see how the electronic engineers can help the community of optical wireless communication.
I'm more than happy to think along and to try to characterize what's really happening. I think it's an interesting question. It's something that we see the other side of. So very often the amplifiers are nonlinear as well. Right? And now having a nonlinear load on a nonlinear amplifier is, from an electronic perspective, quite interesting. But
and then it makes a difference whether you try to enforce a voltage on the LEDs or a current through the LEDs. And what I've learned is that an LED is basically electron comes in, photon comes out. So I want to control the current if I want to control the light output.
I agree, So indeed, but on the other hand, if you have 1 gigahertz of data coming across a quarter lambda transformer or transmission line, then you have a current source.
Yeah.
So
Or
it
if
could
we really
be
try to
that's-
match it by inserting a resistor to make sure that the amplifier sees 50 ohms.
That
This
is,
costs
you would
10.
have to insert an attenuator. Just a resistor will not guarantee that. If you put 50 ohms in series of a transmission line and the thing you put it in series with is not 0 ohms, then you still have no termination. If it's very low impedance, yes.
Yeah.
But I think depends on how deep you want to modulate the light. If you want to modulate it just 1%, then the impedance will be more or less linear and it will be more or less constant. If you want to have a deep modulation, then you will see the impedance over time going all over the place.
Being a nonlinear device.
Yeah, I mean, that's what it's...
And then I see a lot of use of OFDM, which is a modulation method that is pretty notorious for nonlinearities because we get all the crosstalk between the different subcarriers. So the interaction of the electronics with the modulation method is a very interesting thing there.
Yes.
But the LED is not just what we're seeing here, like dynamic resistance.
No.
There are capacitances, it's reactive, and so on.
It's really interesting.
Interesting to measure. We need to do this to build efficient designs. If I need to feed a signal into this, what would be the most efficient? To what should I match it?
Well, that's depends on what you're trying to achieve. But in general, if you want to get most energy into this, you need to match to the conjugate of the total impedance. That gives most energy going into this. Where this energy ends up is a different question. You have 3 places where it can go. Right? It can go to R1, to R2, and to RA.
But RA is the one where electrons get
converted into LED. So that's where you want your power to go.
Yeah.
But now you don't know exactly where it goes. It's frequency dependent, right? At lower frequencies, all the current that goes into the inputs will go to RA. So then it's just a ratio of resistances.
Yeah.
At higher frequencies, some of the currents will go through C1 and CA, and they will not even get to RA.
But can I steer where the power goes by playing with the input impedances?
Only to very limited degree. So what you can do is you can affect the time constants of the first pole, R1, C1. What happens after that, you have very limited impact on.
Mm-hmm. Although when we go to 6G, low power devices, the Internet of Things, the objective may be to make it most efficient.
And we might be able to do things. Right? If you don't look at this in a passive way, but in active circuits, in theory, in electronics, we can make circuits that behave like a negative inductor. Right? If you put such a circuit in series, then L disappears. We can also make circuits that act like a negative resistance. Put that in series, R1 disappears. Right? And so I can, step by step, I could get closer to RA, or I could get completely to RA by negating all the other components. That way I have full control over what goes into RA. That doesn't mean that nothing is dissipated into this, because there's now power still going into this and in the circuits making the negative impedances.
Now basically here you say we can do that with electronic circuits, not with discrete coils and inductors, over a bandwidth from 10 Hertz to a gigahertz.
In theory, yes.
In theory, yes.
There's always practical things, but in principle, yes, you can make circuits like that. In principle, you can make it very wideband, even from DC all the way up.
You said if you want to match it, if you want to achieve these objectives, if I want to go for the highest efficiency, should I just connect a pure voltage source or pure current source to this and make that as the most efficient thing?
No, I don't think there's such a simple answer. I think that you probably want to compensate for the time constants in here. Because if you have data coming in, modulated data coming in, then it will contain a whole spectrum, right? We're talking about OFDM. The different parts of that spectrum will, for different amounts, end up in RA. And that's probably not what you want. And so then you're going to lose efficiency because you're going to put in enough power that the weakened parts of the spectrum still end up in enough light variation. So I think to do that efficiently, you probably want to have a compensation, let's say a sort of a pre-filtering with the inverse of this filter, to make the frequency transfer from the source of your data to RA, to make that frequency independent, to make that flat. because then you have the full benefit of your modulation. And then you end up with something that's not quite a current source or not quite a voltage source, but something with a complex source impedance that compensates for this impedance.
And now I hear the voice of an electronic designer coming back from information theory, where we have all kinds of water-filling theorems. There the theory says you should not put too much effort on the frequencies that are underperforming. So if you have a good throughput on certain frequency components that are transferred nicely through this system, there you put most of your power, and you put less power on other parts. And that becomes then a Lagrangian optimization. And maybe we should meet someday to see where this water-filling optimization of OFDM systems can meet together with the design of an electronic system.
Now, the water-filling, I truly believe. I mean, that's a good idea. But the question is, if you also have the possibility to flatten the transfer curve in the frequency domain, then it still will not be perfectly flat, right? So you still will do water-filling, but the question is, how much improvement do you get? Right? So then you can have a more even distribution of your power, and that might be in the end more efficient, because if you, for example, with water-filling, you would put most of your energy at the high frequencies, then you're going to bypass the RA by these capacitors C1, CA, and that would not be very efficient, right? Because then you lose some signal there. I think it's maybe, I could imagine, but I don't know for sure, that by combining them you can end up better than just by purely taking whatever the transfer curve, frequency transfer curve of the LED is, and then adapting your modulation to it. But that's, I don't know, I would like to find out.
Okay, intriguing concepts. There is also the aspect of all these Lagrangian optimizations have a constraint.
Yes.
Total power.
Yeah, of course.
And then all the electrical engineers that I'm reading the papers of say the electrical power is sigma squared. The expectation of the square of the signal. But we have a very nonlinear device.
Yes.
An LED is like a constant voltage.
Yes.
So the power that goes into the LED is that constant voltage times the average of the current.
Yes.
And not the average of the current squared.
No, and indeed, and it's So that and there's an additional nonlinearity if you're not careful. If you exceed the maximum voltage or current, in this case the current, then it will not be just nonlinear but also time variant. Right? It will break.
Yeah.
I'm not sure that this assumption is really the ultimate optimum that you can achieve.
Yeah. Although there, my argument would be, in 1972, there was a famous paper in information theory stating the peak limited channel, like an LED, for example.
Yeah.
And of course, an LED breaks if you run above the thermal limits.
Yes.
Nowadays, most of the LEDs that we have in the ceiling everywhere are optimized for the highest efficiency and not running them up to the limits of the power.
True.
And that means that there's quite a lot of room to go beyond this optimum. And in OFDM, if you transmit at a gigabit per second, these pulses, short pulses, are microseconds, nanoseconds.
Yeah.
And you don't heat up the LED and kill it in a nanosecond, I would say.
No, I think you're right. That's definitely a good argument. So if there's headroom there, and I think that's indeed, that seems like the logical thing to assume. And then there's chances are that you won't break it so quickly. I don't know anything about the failure mechanisms of LEDs. In electronics, it's not always just the thermal effects. It can also be electromigration, for example, in the interconnect. So it could be that there are other effects as well, but that I really don't know.
I think it would be great to continue to work on this. All these new limitations that differ from radio communications.
Yeah.
Light intensity is non-negative.
Yeah.
We have non-linear relations between the voltage and the light output, the voltage and the current. We have a lot of weird things in the impedances, weird things, I mean, not fully understood, not fully modeled. And they are making a joint optimization with what OFDM can do, tolerating some distortion and so on.
Would be nice, yes.
You already have a PhD, otherwise that would be at least of that.
I think there's no law that says you cannot have two PhDs, but I'm not sure that is the ambition I have at this moment.
Yeah. But it's certainly a topic that in my research I'm really intrigued about, because I do think that Optical wireless communication can borrow a lot from what we know from radio communication with all the antennas. But LEDs are not like an antenna. And seeing how we can do better, improve things, lower power, is where we can gain a lot. Not only by matching impedances.
Yes. Yeah. Oh, definitely. Yeah.
Peter Baltus, thank you very much for joining us today and debating what we can do in optical wireless communication with or without impedance matching, or with all kinds of other ways of improving the system.
Thanks, Jean-Paul.